with type-safe extraction.
Thank you. So, we here at WITS are known to implement type systems. I think it's safe to say everyone in the room has implemented a type system. Most of us would have attempted to implement a dependent type system. So take your favorite dependent language, for example, Rocq, Agda, Lean, just Martin-Liff type theory in general. We all know that to type check these dependent languages, we also need to evaluate open terms at type checking time. This evaluation works for type checking, but is not at all suitable for evaluating programs at runtime. It's massively inoptimized. Implementing optimizing compilers is really hard. So instead of doing it ourselves, what we normally do is we have some program extraction, where we go from translating a nice dependent language into a non-dependent target. So Rocq extracts its program into a camel, Agda extracts into Haskell, Lean extracts into C or C++, I think, I'm not really sure, and Idris extracts into Scheme. So this non-dependent target still has some fancy type features, like often it has some type level functions, it has fixed points, and it has type classes, for instance. But the problem with this type extraction is that it often has to introduce typecasts. So there's the normal justification for why adding typecasts is OK, is that we checked it at the dependent level, and it's perfectly fine. So it must be fine at the lower level as well. And that only works if we only ever run our program with other dependently extracted code. If we ever attempt to try and run with unverified code, then the typecast might no longer be safe. The best result we have was presented by Forster et al., which says that in Rocq, if you have first-class functions on first-class data types, then the extraction shouldn't crash. But that's no use for when we have all our nice dependent types with all their nice high-level functions. So what we ideally want is we want a new dependent language where the extraction process is just erasure of type information. It doesn't change the program in any meaningful way. It doesn't even add typecasts. All it does is it says, hi, types, we no longer need you, it's fine. So in this talk, I'm going to introduce Extractly, which is a new language that I'm in the process of designing, where program extraction is nothing more than type erasure. So here we have a nice triangle. We have two sides which point to the same base, but there's no relation between the dependent languages and Extractly so far. So I conjecture that there's a sophisticated translation between MLTT and Extractly. So the main feature of this sophisticated translation is that our target language, is that the source language, MLTT, has large elimination. This is where types can depend, this is where you can pattern match on data values to produce types. Extractly does not have large elimination. This is one of the main sources for needing typecasts in your non-dependent language. So I conjectured there's this sophisticated translation. I've managed to construct the translation on all the examples I've tried. I don't know if it generalizes to more than those examples, but they include some pretty nasty things, such as the meta-circular evaluator of simply type lambda calculus and things like heterogeneous lists. So I'm going to start by explaining what Extractly is and what its features and non-features are, and then I'll go into discussing the sophisticated translation. So as I said earlier, this is all work in progress. So currently, the only thing that's been done is the type checking of Extractly. The erasure process has yet to be defined and implemented. I'm also missing a formal definition of the source of Extractly as a language, and also proofs and implementation of the translation from these calculi into Extractly. If you want to try the program for yourself, there's a big QR code on the screen for you to go to the GitHub repo where all of this is implemented. So Extractly is inspired by Polarity, written by Binder et al. For, I think it was ICFP or UPSLA 2024. Extractly has the normal data types that you'd see in a regular language. So on the screen, we have the definition for natural numbers, where it's a regular data type with a constructor for 0 and for successor. But we also have codata types. This is like traits in Rust or co-inductive records in AGDA, where codata types are defined by their projections. So a pair is a codata type with a projection for its first component and for its projection for its second component. Codata types don't have a canonical constructor. Instead, they are implemented by codefinitions. We'll see examples of that later. So a consequence of having these codata types is that pi types are now definable instead of being built in. So on the screen, we also have the definable codata type for functions, which given types for the domain and codomain, it has a single projection called apply, which takes the value of the domain type and gives you something of the result type. An extension to extractly compared to Polarity is the introduction of a universe hierarchy. This is standard universe hierarchies. If you have a codata type where one of the projections is large, then you have a large codata type. What's interesting about extractly is what it doesn't let you do. So the first thing that is excluded in extractly is that all data type definitions must be small. So for example, the anything type on the board, where we have a something, which takes a type and an inhabitant, that is invalid in extractly. The reason why this is invalid is that if we go to a non-dependent target, we'd have to introduce a typecast for the something constructor into some universal type. Typecasts are bad. We don't like typecasts, so we can't allow this anything type. Another thing that's invalid in extractly is large elimination. So the example I've given is for defining vectors by pattern matching on the length of the vector. So the zero length vector is just the unit type, and the success and a length k plus 1 vector is a pair of an element at the type A and a length k vector. This is invalid in extractly because if I want to use this type, I'd have to introduce a typecast. If I want to have a function returning this type, I'd have to introduce a typecast. If I want a function consuming this type, I'd have to use a typecast. This is because unit and pair are just not the same type. They're completely different things. So how do we get around the lack of these features? First, how do we... I say that getting rid of large elimination is not a bad idea at all. So I conjecture that the name, as in whether it's like the top level constructor for the data or codata type, does not depend on the value of 3 variables of data types in your context. So instead, it can depend on the values of codata types. So here is a slightly contrived example on the right-hand side about how the names of types can depend on codata types. So at the top, there is the codata type for an index family of sets. So it takes a set of indices A, and for each value of A, it produces a type that's indexed by that value A. We can then iterate that construction so you can have a family over families as a type. For example, and then we give an example of at point, which given a type and a value of that type produces a family of families of that type by taking each family F and finding out the type at the point X that we were given earlier. So for codata types, the top level name of a type can depend on codata values, but this computation can never depend on the runtime value of any data type. This is only a conjecture because there's been no formalism, so I can't even state the formal statement. So that is what extractly lets you do. It lets you have these codata types and data types. It doesn't let you have large elimination. So how can we translate nice regular MLTT and dependent types into extractly? So to get rid of to sort out the definable functions, we can use work by Ahmed and Bowman or by Huang and Yallop, which does defunctionalizing of dependently typed languages. So that's a big step in the right direction. But the actual elimination of the removal of large elimination is, I think, novel. So let's start off with an example. So here is an example of vectors again. So on the left, we have the pattern matching definition I gave earlier. So where we pattern match on our value of nat to determine the type of the vector. So as you can see, when the length of the vector is 0, we have the unit type. We can translate this into an index data type, where for the nil constructor, we have a vector where it has no data associated with the nil constructor, and its associated length is 0. Likewise, for successor, if the length of the vector is successor of k, then we have a pair of a value and a shorter length vector of length k. So we can encode this as an index data type by having a constructor with 2 arguments, the new value and an inductive and a recursive vector, inductive vector, and that constructs a vector of length successor of k. This generalizes to more complex examples. So on the slides now is the Agda definition for a interpretation of simply typed lambda calculus types within Agda. So a type of the simply typed lambda calculus is either a base type from some set X, or it's an arrow type between 2 other types. And given a family over base types, we can construct a family over types, where at the base type we use our given family, and for arrow types we interpret that as a function between 2 interpretations. We can, because this uses large elimination, because we're pattern matching on types to define our interpretation function, which is a large set. So instead, we can reuse index data types. So again, we need the codata type of families. But given a codata type, given a particular family, we can in turn define our index type of interpretations over lambda calculus types. So for base types, we will use just the value. We'll give a witness that the type inhabits the given index family. And for arrows, to define our interpretation on arrows, we need to have a function that translates from interpretations of A to interpretations of B. There's nothing complicated about this individual slide.
I feel lost. What's the base and arrow in the return type of the constructor?
So the base and arrow are the names of the constructors for the type of A of tie of X.
They occur once in constructor position and then once in the return.
I've overloaded the names without telling you.
So what are the base and arrow in the return type of the constructor?
So the base and the arrow are the constructors for the tie type, and the so this base is the type. It is the constructor for this type.
Okay, so that means that I cannot use the base type, which is an arrow. Before, in the interpretation of the slide before,
Yes.
you can have a base type whose interpretation is A to B.
You can't have a base type whose interpretation.
Yes.
You can't have a base type whose interpretation is A to B unless that's what P says it should be.
Yes.
Yes. And that's the same case here.
I think you're missing an arrow set there.
I am missing an arrow set here. You are correct. Does that help?
I'm not sure.
OK, I'll continue. So there are some downsides to getting rid of large elimination. The first of which is that we introduce a lot of singleton pattern matches. So in the Agda example, recall how the interpretation on functions was itself a function type. Now, in our extractly definition, the interpretation of functions is just a value of a data type. We first have to pattern match on that value to be able to extract the function from it. So for example, to apply our interpretation for arrow types to an interpretation for the argument, we first have to pattern match and get the singleton case that we have an arrow, and then we can apply the function argument. Whilst this can be optimized away, it is an extra step of pattern matching that wasn't in the source program, so it's harder to write programs in that sense. Another limitation is that for the construction I just showed you, because data types must be small, the indices over them must also be small. So a standard thing you can do is construct a heterogeneous vector over a list of sets, where if you have the unit list, then you have the unit vector, and if you have cons, then it's a pair of the first type with the rest of the vector. We can't use the same translation as I just showed you, because we can't even define list of set in extractly, because that data type is too big. So instead, you have to do some extra manipulation, which is, I think, possible, but I have no idea if it is or not. I'm willing to take all your examples to try and test whether or not this translation is possible in general. But it is a limitation compared to having large elimination. So there are some potential extensions that we could take with this work in progress. So one idea is to split values into atomic and complex values. So atomic values are values that live on this that can live on the stack. They take up the same amount of space no matter what. For example, these are primitives and pointers to elsewhere on the stack, or to elsewhere in memory. And then complex values are things that have to be pattern matched on. So data types will be complex values, as would be, but closures to codata types would not be complex values. This is possible because extractly and Polarity has this strong distinction between data types and codata types, and because we don't have to, and because we have definable functions instead of first-class functions. So another potential extension is to introduce an effect system. So on the slide, it is an example where we have a hello world function, which returns a unit type, but uses the print effect. So where first we print the statement hello world, and then we return the value from printing hello world. Again, this is possible because we have a strong distinction between values and data types and codata types and computations. Another potential extension is to introduce consistency to the language. So Polarity is not consistent. Polarity, which extractly is based on, is not consistent. Polarity explicitly has type in type. So we have Russell's paradox. The reason why they don't care about consistency within Polarity is due to their specific use case of trying to explore the duality between data and codata types. In extractly, I don't care about that duality anywhere near as much. So I've already introduced the universe hierarchy to determine what small data types are. So we can also plug in off-the-shelf termination and progress checkers to check for consistency. There is one more extension that a consistency checker will need, and that's to do with the type indices. So if we recall our example of interpretations, here we have a negative occurrence of the interpretation function, but the type index is structurally smaller. So it should still be sound, no matter, even though there is a negative occurrence. So we would have to extend termination checking to include these induction over the type indices of data types. So to summarize what was in the talk, I've implemented extractly, where extraction from extractly into a non-dependent target should just be type erasure. I have demonstrated a translation from some examples of large elimination back into extractly without large elimination. And I'm also looking for a job because I'm coming right up to the end of my PhD. So thank you.
Questions? Let's thank the speaker. Oh, there is.
I think you didn't mention this. Did you also think about extracting again from extractly? Like, did you implement extractions to other programming languages?
I have not implemented the erasure from extractly into a non-dependent target, but it should be simple.
Okay.
I
okay.
expect. It should only be erasing type information. It shouldn't introduce any typecasts.
And if you have code data, so for instance, you had this interpreter function.
Yes.
Yes. If you extract this, you hope to get again, say if you extract this to OCaml, you hope to get again a recursive function in OCaml.
So if I extract this data type, this should just produce a regular OCaml data type, but without any mention of the type indices.
Yeah. So it's not executable as an OCaml program afterwards.
But neither was this executable as an OCaml program. This produces a type which isn't a program.
Right. Okay. So if you imagine again an interpreter that finds normal forms.
Yes.
In this, you have to write it down also as code data, right, or as data.
So if you want to find if you want an interpreter that finds normal forms, you'd implement a function that returns something of this type, possibly. So for extractly, you'd introduce a function that returns something of this data type.
Okay. So in particular, you get a runnable OCaml function in the end.
Yes, functions extract into functions. Code definitions extract into records of functions or modules.
Okay.
It's only the data types that get type erased.
Okay, cool.
Other questions? Okay, thank you very much for the nice talk.